Okay, so we've talked about linear transformations in general. We've talked about how to find matrices of linear transformations. So in this video, we're going to talk about kernel and range of linear transformations. And then later on, when we do some examples in class, we will tie the ideas of finding kernels and ranges with the ideas of talking about matrices of linear transformations that we've discussed before. So let's do a definition. So we have a linear transformation from V to W, and of course, like always, we're going to assume that V and W here are representing vector spaces. Then the kernel of T, which is, we got right, KER of T, but I will always say kernel, is the set of vectors in V, so everything in the domain that maps to 0 in W. Okay. All right, so let's do a specific example. So let's say we have the transformation T that goes from R2 to R. We're going to define this transformation by sending the vector xy to just x. Or think of it more generally, we're going to take the vector xy, or the point xy, and map it to its x coordinate. Okay? So then it's not too hard to see that the kernel of this particular transformation is, well, if I'm going to map it to 0, because that's what the kernel says it has to be, then the x coordinate has to be 0, and since the output doesn't depend on y at all, then anything of the form 0, y will be in the kernel. So as a picture here, so here's the R2, here's the Cartesian plane. If we take a point 0, y, anything on the y-axis, we're going to map it to, again, its x coordinate, essentially. So everything in the plane gets mapped to the real axis. So this is just a geometric picture of what's going on for this particular transformation. We refer to this as projection onto the x-axis. You could define a similar one as a projection onto the y-axis. Just change your T of xy to equal y rather than x, and you would have projection going this way onto the onto the y-axis. And then you could see pretty quickly that everything on the x-axis is in the kernel. Everything on the x-axis in this case, in that case, would get mapped to 0. All right, let's do another example. Let's say we have the transformation from polynomials of degree n or less, and then going to again to the reals, where the transformation is p of x is equal to p of 0. Okay, so this is sometimes referred to as an evaluation transformation. We're just going to take, I'm going to plug in 0 for the x. Then the kernel here is anything that when you plug in 0, you get 0 out. Okay, well, if I'm going to plug 0 in for x into a polynomial, that's going to kill all of the powers of x. The only thing I would be left with is the constant. So the kernel here must be the set of polynomials that have 0 constant term. So, or said another way, anything that you could factor x out of. All right, let's look at another one here. Let's look at a transformation that goes from R2 to R2, and we're going to define this by negative, it's going to be multiplication by the matrix. So 0, negative 1, 1, 0 times the vector. Then we have the kernel here is just the 0 vector. Let's see why that's true. So notice that if we just went ahead and carried out the matrix multiplication, if we did T of xy, if we imagine putting an xy here as a column for your V, then what you would get out is negative y x. So if I want to get out 0, 0, because remember the kernel is everything that maps to 0. So if I want to get 0, 0 out of the transformation, then x had to be 0 and y had to be 0. So the only way to get 0, 0 out is to put 0, 0 in. So another thing you can notice here is that if I take the xy and take its dot product with the negative yx, we get 0. So that means that our output here is orthogonal to the input, right? When we take the output here in R2, it's orthogonal or perpendicular to the input. So one of the things that we can notice is that essentially what we've done is we've taken the vector and rotated it 90 degrees counterclockwise. All right, So let's talk about a particular property for the kernel. We're going to do more properties of the kernel and the range later on, but in particular kernel. So one of the properties for the kernel is that it's always a subspace of the domain space of V. So let's go through our subspace check. We did this back in chapter 5. So we know for the first thing we have to make sure is that our set is non-empty, right? Our purported subspace is not empty. So let's make sure something's in there. Well, we know something that always maps to the 0 vector in W, it's the 0 vector in V. So I know that the 0 vector is definitely in the kernel, so it's not empty. So remember, to show subspace, we have to show that it's closed under addition and closed under scalar multiplication. So let's take two vectors in the kernel and a scalar and show that it's closed under those operations. So transformation applied to x plus y. Remember, the defining characteristic for being in the kernel is that the input maps to 0. That's the defining characteristic. So I need to show that x plus y maps to 0. That's why I'm applying the transformation to it. All right, so using our property of linear transformations, I can break up the transformation over the sum. Each of x and y are in the kernel. That means when I apply the transformation to x, I get 0. And when I apply the transformation to y, I get 0, which gives me 0 out. So that tells me that x plus y is definitely in the kernel, because when I applied the transformation to it, I got 0. Same idea for the scalar multiple. Let's apply the transformation to the scalar times x. By our properties of linear transformations, we can pull the constant out in front. So I get c times the transformation applied to x. Again, x is in the kernel. So the transformation applied to x is 0, and then any constant times 0 is 0. So the scalar multiple of x is back in the kernel, and that tells us that we really do have a subspace. Okay, so let's switch over to range. Again, transformation from V to W, then the range of T, when we denote that RAN of T, but I'll say range each time, is the set of all outputs, set of all possible outputs of the transformation. So it's just you take any vector in V, apply the transformation to it, and look at that as an entire collection. That's the range. So let's look at a couple of examples again. This was the first example we looked at in kernel, the projection onto the x-axis. Well, then the range is all of R, okay? Because if I want to get an x out, well, to get the x out, I could just plug in x comma 0. There's lots of things I could plug in, but in particular, I just need to plug in x comma 0. I just need to find one thing to plug in to give me the output that says that it's in the range. In this case, since our range was equal to our codomain, we say that T is onto, because everything in R has an input that yields that output. So no matter what I pick in the reals, I can find something in R2 that maps to that particular number. All right, same idea here. This transformation. Well, I think the range here again is all of R, because notice that one of the subsets of Pn are the constant polynomials. So if I pick a constant in R, then let that polynomial equal that constant polynomial, then certainly if I plug 0 into the polynomial, I get C out. So again, we have another onto transformation in that case. So let's look at something that's not onto, since everything we've done so far is onto. Has been onto, I should say. So let's do this transformation where a point x comma y gets mapped to x comma 2x. Okay. Well, let's see what happens with geometrically. So notice that I'm taking any point and I'm mapping it to the same x coordinate and double the y coordinate. So let's just look at these 2 points that we have here. Here's the point 1, 4. I get mapped to the same x coordinate. That means those 2 points have to be on the same vertical line But instead of the y-coordinate being 4 now, the y-coordinate is double the x-coordinate. So that's why it gets mapped down to 1, 2. And in particular, anything on this x equals 1 line, we get mapped to the point 1, 2. Likewise over here, if I look at the point -2, 3, at this point here, the x-coordinate is -2, so it gets mapped down here. And then again, the y-coordinate is double the x-coordinate. So in this case, it looks like a projection, but instead of projecting onto the real axis like we did before, we're projecting onto the line y equals 2x. So in this case, this is not onto, because I did not get every single vector in R2 out. The only vectors that I can get out are the ones where the y-coordinate are double the x-coordinate. All right, so quick algebraic property of the range, and then we'll save more examples and other properties for class. If we have a linear transformation, then the range is a subspace of W, has to be in W in this case, has to be in the codomain because we're talking about outputs. Do the same kind of thing that we did for kernel. The first thing we have to show is that the range is not empty. Well, certainly, no matter the linear transformation, we can always get the 0 vector out of it. So the 0 vector is always in the range. So now, again, like we did for kernel, start with 2 things in the range and a scalar in R. Since x and y are in the range, that means that they are outputs. Okay, well, to be an output, you have to correspond to an input. So there must be vectors u and v, so that when I plug u into the transformation, I get x, and when I plug v into the transformation, I get y. Now I need to show that I need to show that x plus y is an image. I need to find something to plug into t so that I get out x plus y, so that x plus y is in the range. Well, the likely candidate here is u plus v. Plug in u plus v into the transformation. Transformation splits up over the sum. And then, of course, the transformation applied to u gives me x, and the transformation applied to v gives me y. So I really do see that x plus y is an output of the transformation. So x plus y is in the range. Likewise, do the same thing for the scalar multiple. This should say a u here, not an x. This should be a u. The transformation applied to c times u is c times the transformation applied to u. And then this line is correct. This is c times x. Change these in the first line to u's. And then I have c times x, and so I really do see that c times x now is in the range. So if I plug in c times u, I get c times x. So c times x is in the range, and so the range is a subspace. Like I said, we'll do more examples of this stuff in class. Also tie this into looking at matrices of the transformations as well.